Okay, so to finish the material for this week and material needed for the exam, we go over the product and quotient rules. These are rules that allow us to obtain the derivatives of, well, the rules say, products and quotients. And the product rule tells us that if you want to take the derivative of a product of two functions f and g, then you need to do the following here. Compute the derivative of the first function multiplied by the second one without differentiating plus the first function times the derivative of the second one. Uh, and I want to stress this very strongly, something that we see very often with many other instructors is that students try to differentiate something like f times g, and they claim that this is equal to f prime times g prime. This is absolutely wrong. This is not how this works. So if you want to take the derivative of f times g, you have to proceed by applying this rule. You're going to have two terms. One where you take the derivative of f and multiply it by g, and then another term, the second one where you take just the derivative of g and multiply it by f. So that is how it works. So anything like just multiplying the derivatives of the two functions is completely wrong and can be immediately observed from the fact that if that would immediately imply that the derivative of any function would be 0, because any function f can be written as 1 times f. And so if you were to believe that formula that I just told you was wrong, this would correspond to the derivative of 1 times the derivative of f. The derivative of 1 is 0. So this will tell you that the derivative of f is 0 for any f, which is clearly not correct. Okay, so avoid this mistake at all costs. I mean, that is whenever we are asking you to apply the product rule or differentiate something, and you need to use a product rule, or it is implicit that you need to resort to apply the quotient rule. If you proceed by differentiating the product like that, just taking the product of the derivatives, then that's no points at all. I mean, you will not get any partial credit, because this is something we insist on every single time. The same thing is true for the quotient rule. So if you want to take the derivative of f over g, you have to apply this rule like this. So you just take the derivative of the first function, the function on the numerator, times the function in the denominator, minus f, also the function in the numerator, times the function differentiated, so the derivative of the denominator. And all of that is divided by the denominator squared. So that's why we require g of x to not be equal to 0. Otherwise, this is not going to make any sense. Okay, so the rule doesn't apply there. In fact, the function will not be even differentiable at that point. Okay, so this rule only applies when g is not equal to 0. F and g, of course, have to be differentiable for both rules to apply. And yeah, so the mistake here to avoid is saying something very, making the same kind of mistake that I just mentioned for the product rule. That means to claim that if you have a quotient like this and you want to differentiate it, you just simply need to take the quotient of the derivatives. Again, this is not only wrong, this is super wrong. Will lead to many contradictions if you wanted to apply it like this. Okay, so you just follow these two rules. They're fairly simple, and the first one is very symmetric, of course, because f times g is the same as g times f. And the breaking of the symmetry here comes from the fact that numerator and denominator need to be treated separately. But once you know these rules and learn to identify when to apply them, everything is just routine. So let's see some examples. Some examples for the, say, the product rule. So first one, what is the derivative of f um, where f, so let's rephrase it. So find f prime of x where f of x is equal to e to the x times x plus 1. So what is a derivative of f in this case? So we apply the product rule. So the solution here is to apply the product rule. So we apply the product rule, right? Because f prime will be equal to the derivative of the product of two functions, e to the x. This will be our first function times x plus 1. This will be our second function. Right, so we want to differentiate that, then remember, what does the rule say? We take the derivative of the first one, in this case e to the x, so e to the x prime, times the second one, x plus 1, not differentiated, plus e to the x now, which is left untouched. We don't differentiate it, but we take the derivative of x plus 1 prime. This is in complete agreement with the formula up here for the product rule. And then, well, what is the derivative of e to the x? Is just e to the x itself, and x plus 1 is simply x plus 1. Now, plus e to the x times the derivative of x plus 1, but here we apply one of the other rules. So when you take the derivative of two functions that are being added together, we just take the derivative of each one and then add add these two derivatives together to obtain the desired result. I mean the derivative of the sum of these two functions. The derivative of any constant, in particular 1, is 0, so this is just 0. And the derivative of x, this is part of the power rules, this is just 1. So all in all, we end up with e to the x times x plus 1 plus e to the x times 1. We have a common factor of e to the x, so we can write this as e to the x times x plus 1, which will come from the second part, so we just end up with e to the x times x plus 2. If you remember one of the problems for the list of problems for last week, where we asked you to find the equation of the tangent line, I gave you something as a given that the derivative of a certain function was equal to that. Well, that actually applied the product rule. So, and what's the point I'm trying to make here? You may be asked to use the product rule as part of a problem, not directly. I mean, we may not ask you to say, we may not write it as apply the product rule to find this derivative. But if you're asked to find the equation of the tangent line, for instance, and the function you're trying to find the equation of the tangent line of you need to differentiate, you need to take derivatives of, may be defined as a product, and therefore you will need to apply the product rule, even though the problem may not state it that way. Okay, so it made this I mean, the application of the product rule may be embedded into a problem, say about the finding the equation of the tangent line. In fact, I believe that this is going to be the case for the exam, for the midterm. you'll be given a function like this, e to the x times something, and you'll be asked to find the equation of the tangent line. So when you do so, well, of course, you need to know a, that will be giving you the point. You need to evaluate the function at the point a, but then you need to find the derivative at the point. And then you will, in order to find that derivative, you will need to use the product rule and finally evaluate at the given point and plug that into your formula for the tangent line. So it's very important that you learn to recognize when you need to apply the product rule or when you need to apply the quotient rule. This is kind of immediate here because I've written f of x as the product of two functions. So there's no way of getting confused here. And it's probably going to be the same thing for any application of the quotient rule. Well, let's go over another example. Now applying the quotient rule. So we may be asked to find, say, the derivative of f of x, or just, let me just define it as g of x now. G of x equals to x plus 3 divided to x by x to the fourth plus 5. So it's a simple question. Find the derivative of g of x. In fact, this function will be differentiable everywhere. Why? Remember that the only problem that you may encounter when trying to differentiate these functions or trying to see where it may fail to be continuous or differentiable is when the quotient is not defined. So when the denominator is equal to 0, but x to the fourth is always positive, and you're adding something, or it's always non-negative, so it's always greater than or equal to 0. It may be 0 when x is equal to 0, but otherwise it will be positive. And if you add a positive number like 5, then the resulting number will be positive. So the denominator can never be 0. So this function will be differentiable everywhere. Okay, so you'll be able to apply the quotient rule to find the derivative of this function actually at any point. So the solution, so we apply the quotient rule. We apply the quotient rule. So now we have two functions. So we, of course, if we want to take the derivative of x plus 3 divided by x to the fourth plus 5, we immediately see that there's a function at the top and a function at the bottom, and they're both polynomials. So that means that we can differentiate them because we already know how to differentiate these functions. We already know how to differentiate polynomials because we know how to differentiate power functions, and we also know how to take the derivatives of sums of functions, so the sum of two functions and sum of several functions. So what does the rule say? So what we have to do is we have to take the derivative of the function at the top, so x plus 3, multiplied by the function in the denominator, x4 plus 5, now minus x plus 3, so the function in the numerator, just like that, and times the derivative of the function in the denominator, all of that divided by the function in the denominator square. This is just the way the formula works. If we go back to the formula, just a couple seconds, so the derivative, so f over g differentiated takes on this form when you expand everything. So to obtain f over g prime in terms of f, g, and f prime and g prime, g, f prime and g prime, you apply this formula here, and that tells you that again is you have to multiply the derivative of the numerator times the denominator minus the function in the numerator times the derivative of the denominator. All that divided by the function in the denominator square. And this is exactly what we've written here. Now, the derivative of x plus 3, again, was just the derivative of x plus the derivative of 3 by the basic rules of differentiation, meaning we can add the derivatives of these two functions to obtain the derivative of x plus 3 separately, and then add them together. And then f minus x plus 3, x to the fourth power prime plus 5 prime. All of that divided by x to the fourth plus 5 squared. Now, x prime is just 1. 3 prime, remember that the derivative of a constant is 0, so this is just 0. And here x4 prime, x to the fourth prime, is just, we just apply the power rule, so we obtain x to the 4 times x to the cube. And 5 prime, again, a constant, differentiated gives us 0. So we obtain here 1 times x to the 4th plus 5, so x to the 4th plus 5 minus x plus 3 times what's inside, so 4x cubed. All that divided by x to the 4th plus 5 squared. This is equal to then x to the 4th plus 5. Be very careful. So that's why I just want to go over them. I mean, this is elementary arithmetic, but I've seen some mistakes in some of you when you develop what's inside a parenthesis once you bring the minus sign inside. So this is equal to minus 4x to the 4th power. So in fact, let's just not skip any steps. So I'm going to bring this inside first, and then I'm going to open up the parenthesis. So 4x cubed times x just gives us 4x to the 4th plus 3, and now I multiply this by that. I distribute everything, and I get this times 3. So it's 3 times 4, which is 12 x cubed, and all of that divided by x to the 4th power plus 5 square. This is equal then to x to the 4th power plus 5 minus 4x to the 4th minus 12x cubed. Once I bring this minus sign inside, it flips all the signs around inside the parentheses. All the signs inside were positive, so they all turn into negative expression. So 4x to the 4th and 12x cubed, they're both turned into negative. They're minus these expressions. Minus what there were before. X to the 4th power plus 5 square, still on the denominator. We see here that we have like terms, and this gives us minus 3x to the 4th minus 12x cubed, which is this term over here, and finally we have a plus 5. And all that will be divided by x to the fourth power plus 5 squared. Okay, so that's an application of the quotient rule. Let's go over another application of the quotient rule, but now with some other functions. Again, the same question. So find the derivative of f where f of x is equal to say the square root of x divided by e to the x. And I wanted to go over this example because you can, even though, I mean, for some of you may be very clear why both rules apply in this case. For some, it may not be evident, but you can in fact apply either rule to try to compute this derivative here. So it is written as a quotient, so we may as well use the quotient rule. So this is the first solution. We apply the quotient rule because we have square root of x divided by e to the x. So that f prime of x will be the function at the top, square root of x prime times e to the x minus the square root of x, just like that, times e to the x prime. All of that divided by e to the x squared. Okay, so now we find the derivative of the square root of x. Remember, this is just a power function. We talked about this last week. So alpha here is 1/2. So this is x to the 1/2 prime times e to the x minus x to the 1/2 e to the x prime. E to the x prime is just e to the x. We already know that. When we take the derivative of e to the x, it just gives us e to the x divided by e to the x squared. E to the x squared is just e to the 2x. And this is just a property of exponential functions. And here the derivative of x to the 1/2 applying the power rule is 1/2 x times 1/2 minus 1 times e to the x, and then minus x to the 1/2 e to the x, all that divided by e to the 2x. This is the same as 1/2. Well, 1/2 minus 1 is minus 1/2, so you get 1 over 2 x to the minus 1/2 e to the x minus x to the 1/2 e to the x divided by e to the 2x. We have a common factor of e to the x here, so we can write this as e to the x times 1/2 x to the minus 1/2 minus x to the 1/2, all that divided by e to the 2x. And here we may cancel one of the e to the x's here, so get rid of that, and we may simply write this using the square root notation. So this is 1 over 2 times the square root of x and this is minus the square root of x. All that then is just divided by e to the x. So this is the first solution. Okay, this is the first solution using the quotient rule because it was given to us as a quotient. Uh, uh, we can also apply, or we could have, the product rule instead by noticing that in that for this problem f of x is a product. How was f of x defined? It was defined as the square root of x divided by e to the x. But this is the same thing as the square root of x times e to the minus x. 1 over e to the x is the same as e to the minus x. So we may apply the product rule. Sometimes that's actually easier, as we will see in this case. So the only thing that we're missing here, and this is why I didn't start with that, is because we don't know what is the derivative of e to the minus x. This will be trivial once we learn something that is called the chain rule. Okay, but for now, so the problem is that we have not learned yet how to differentiate e to the minus x. We know how to differentiate e to the x, but not e to the minus x. That won't be that difficult. We can do it directly by differentiating 1 over e to the x and using the quotient rule. But that will basically amount to doing the same thing we did before, so it won't be much gain to do so. But in the future, once we cover all the differentiation rules, I would recommend that you use the product rule whenever you can, because it's less involved, it's more symmetric, and you see in here there are many things that will become unnecessary once when you apply the product rule instead of the quotient rule. Here we got an e to the 2x at the bottom, which we're able to cancel out with the e to the x on top. I mean, one of the e to the x's. So we have e to the 2x, and we cancel one e to the x on top, so were left with e to the 2x. So the 2 went away, and we just got e to the x in the bottom. And the thing is, if you do this computation using the product rule and what we haven't learned yet, the chain rule, this becomes much easier. Okay, so you don't need to cancel anything out, and so there are fewer opportunities for you to make mistakes. For now, well, you're just stuck with what we have so far, and this is what you need to do. So for the exam, in sum, we we'll be asking you to differentiate some quotient like this. And since it's given to you as a quotient, you have to think immediately that what you need to do is to apply the quotient rule. Okay, so that's just what it is. So you have a formula for the derivative of the quotient. Just apply it, and you'll be fine. Then, because you know how to differentiate, exponentials and polynomials. Okay, so then that's what you do. On the other hand, we may ask you to say find the equation of the tangent line for a product of two functions. So a function is a product of two other functions, each one of which each one when you know how to differentiate each one, so you know the derivative of each one of these functions in this product, and then you may well, knowing the point and the value of the function at the point, you're just left with the task of computing the derivative and evaluating at the point A, and then substituting this into, you're left with the task of plugging this in to the formula for the equation of the tangent line, which is just a formula, and you have completed the problem. But my point is that differentiating something using the product rule may be embedded into a problem about finding the equation of the tangent line, where you need to compute the derivative of the function, and the function may be, it's as part of the problem, but not as the whole problem. It's not just the whole problem, but as a part of the problem, and you need to you need to recognize that the given function is a product, and you need to take the derivative of that. Okay, and as part of the problem, and recognize that you need to apply the product rule and apply it correctly. Again, avoid mistakes such as writing that the derivative of f times g is the derivative of f times the derivative of g. That's completely incorrect. Okay, so just avoid that, and you should have no problems. Okay, the rest that we're gonna be doing this week is gonna be about reviewing the material and going over several problems in order to get you prepared for the exam. Pay a lot of attention to these problems. Some of the problems are going to be very, very similar to what you will see in the midterm, and so make sure to ask with time, in advance, if you have any questions, if there's anything you have doubts about, or you don't understand quite well, or you think you will not be able to replicate in the exam. As I said, everything is been covered thoroughly, the exhaustion. So if you work, if you do your work and go over all the examples we've covered in class, and we solve all the proposed problems, then you should you should do very well in the exam. You should feel very confident that you're gonna perform really well. As I said, if you have any doubts, if you think that you may need more help, or that even though you may think you understand a problem, but you're not quite sure that you will be able to apply it for the exam, then please contact me in advance, okay? So that I'll have the chance to correct any misconceptions and also help you getting more used to using these kinds of arguments that we've learned. As I said, okay, so pay attention for the upcoming videos. They're going to be about the review, and they're going to be covering problems that are going to be very useful for the exam. They're going to be essential, and in fact, they're going to be on the exam. Okay, so thank you very much, and just pay attention to when the review videos come out, and yeah. and pay attention to the announcements as well.